Alright guys, let's finish up this chapter. This should be our last video. So we've talked about the enthalpy of forming a solutions and therefore the factors that affect the enthalpy of a solution and whether the solution will form or not based off of Gibbs free energy. Let's take a little bit further look on some other factors that affect solubility. So the first one is structure effect. This is actually just dealing with the polar versus non-polar stuff we've already talked about. And that, of course, ties back into delta H and all that fun stuff, but just kind of some fun facts here. We have vitamin A over here, and if you look at it, for the most part, it is considered non-polar. Yes, it does have this OH group at the end, which would form hydrogen bonding, but look at the OH compared to the full size of this structure. So overall, it's considered non-polar, and what you'll find out as we move through, if you're planning on taking OChem or anything in the future like that, what you'll find out is there's not as a definitive line between whether something's polar or non-polar, meaning you can have a structure that for the most part is non-polar but does have a polar tail, and overall we say the structure is non-polar. So vitamin A is considered non-polar. We'll check out vitamin C over here. Look at all the OHs and the O's on this, okay? This guy is most certainly polar. Okay, so what does that mean? So, have you ever heard of somebody taking too much vitamins? Okay, and yes, the answer is yes, you can take too much vitamins. You can take too much of specifically the non-polar vitamins, and what that's going to do is it's going to cause these vitamins to deposit into your fat cells in your body. So, if you've ever heard of somebody having orange skin due to having too much beta-carotene or vitamin A, it is because this guy cannot travel or cannot be dissolved in water. Therefore, instead of it going out with your urine, it ends up depositing into your fat cells, building up in your fat cells, which are your skin, or is underneath your skin, and therefore makes your skin look orange. Versus vitamin C, you really can't have too much vitamin C. You'll get sick if you have too much of it, but it's not going to deposit in your skin. It's going to go out with your urine or, God forbid, cause you to have diarrhea over time. If you have too much of it, it will dehydrate you. But for the most part, it's going to leave your body fairly quickly. It's not going to build up, and you're not going to end up with a long-term issue because of it like you could with a non-polar vitamin such as vitamin A. Okay, so structure effects dealing with polar versus non-polar. Okay, we already know that one, and now we can tie that back into understanding that with our delta H's. Okay, we also have the pressure effect. Now, of course, pressure is not going to affect solids and liquids in any way, shape, or form. They're already as compressed as they can be. So what does pressure affect? It affects gases. Okay, so if you've ever been to the Coke factory and you've seen the machinery for how they make the bottles or how they add the Coke to the bottle, they say the bottles are already pressurized. Well, what's the purpose of that? Well, what makes a Coke a good Coke? It's the carbon dioxide, or the carbonation, which of course is a gas and therefore has to be dissolved into the Coke to make it something worthwhile to drink, that carbonation, that bubbliness. Okay, so increasing pressure in a system with a gas is going to force that gas to interact with the liquid. What actually is happening here is a little bit of our vapor pressure, if you will. Because we're increasing the pressure on this, we're going to cause these gas molecules to shift into the solution because there's too much pressure up here. Therefore, it's got to shift back to equilibrium by getting rid of some of the gas, and the gas is going to go into solution. Therefore, more is going to be able to be dissolved in solution if you increase pressure. And again, this is only going to work if you're dealing with a gas dissolved in a liquid. So a Coke, when you buy it, is already pressurized, which means the carbon dioxide is nice and dissolved in there. But what happens as soon as you pop open that top? Okay, well, you're decreasing pressure at that point in time, which is what's going to happen is the gas is going to be able to escape, and it escapes with that shh noise you hear when you open the Coke, the fizzing noise. Okay, so that's pressure, and again, only works with gases. Okay, and then of course we have the temperature effect, and the temperature effect is different for solids versus gases, or different for solids and liquids versus gases. Okay, if you increase the temperature of a solution where you're dissolving a solid or dissolving a liquid, what's going to happen? 9 times out of 10, it's going to cause the solid and liquid to become more soluble. So think back to when we talked about the oil and water. Oil is not soluble in water originally, but if you increase temperature, now the oil is able to dissolve in the water. okay, are, better yet, sugar and water. If you go to a restaurant and get unsweet tea and try to dissolve sugar into it, is the sugar going to dissolve well? The answer is not really. And that's because a lot of times the tea is already cold. But if you have hot tea and you add sugar to it, the sugar dissolves very, very well. And that's because of that temperature, that heat allows for that dissolving process to work better. And again, it does go back to that delta G equation. For gases, though, if we increase temperature, guess what's going to happen? It's actually going to cause less of the gas to be able to dissolve. So think about a warm Coke versus a cold Coke. Warm Cokes are disgusting, and that's because the gas is not able to dissolve very well and it escapes very quickly. Versus a cold Coke, more gas is able to dissolve, and therefore it tastes much better. So think about it this way. What happens if you increase the temperature of a gas? Well, the gas molecules start moving much faster, and therefore they're not going to stay put very well, and they're going to escape wherever they're being put very, very quickly. Okay, so that's the temperature effect. Okay, let's check out this equation, or this problem. This is an AP problem. Benzene, C6H6, which is nonpolar, if we remember the fact that anytime we have carbon and hydrogen bonded together, just as themselves, it's nonpolar. It's only slightly soluble, and pay attention to this word here, slightly soluble, in water, which best accounts for this result in terms of thermodynamics. This is going back to our three-step equation, or 3 steps to form the solution. So the first one is benzene has strong IMFs that release a large amount of energy when broken. Okay, well, we know that's wrong. Benzene's nonpolar, therefore weak IMFs. Okay, benzene is hydrophobic, so benzene and water do not form IMFs between them, so no energy is released. Hopefully, now that we've talked about intermolecular forces, we understand that this idea of IMFs never forming between two things isn't going to happen. IMFs are always going to form between two different species. It's just the strength of those IMFs. So benzene and water are not going to form very strong IMFs. They're going to end up being the dipole-induced dipole, due to the fact that water is a dipole and benzene is nonpolar. So the water is going to induce a dipole in the benzene, but those are going to be fairly weak IMFs. So this one's definitely wrong. There are going to be forces to form. And also keep in mind this word slightly means there is a little bit of a solubility factor here. It is dissolving to some extent, and everything dissolves to some extent if we remember back to our KSP. From there, water has strong IMFs that require a large amount of energy to break. Okay, well that's a true statement. Let's see if that makes sense in terms of everything else. The total process will be exothermic, which is unfavorable. Okay, so if we remember back talking about delta H, we really actually want a negative delta H, which is exothermic, but whether something is unfavorable or favorable really deals with our delta G, not our exothermic and endothermic. Okay, so we're going to go ahead and rule that guy out. And again, that will make more sense when we get to thermochem a little bit further on. It's delta G that makes the determination, which is not exothermic, though exothermic and endothermic play a role. So it's got to be this guy. So why does this guy work? Well, remember our 3-step process, delta H1, delta H2, plus delta H3 forms our delta H of solution. Okay? So when we're talking about water having very strong intermolecular forces, that means that this third delta H is, actually I guess it's going to be our second delta H or our first, either one. It's going to be breaking those intermolecular forces. It's going to require a lot of energy to break, which is going to give us a very large positive delta H. When we form the solution, or when the two come together, the benzene and the water come together, it's only going to give us a small negative due to the fact that it's just the ion-induced dipoles. Or the dipole-induced dipole, excuse me. So not a very large negative, but a very large positive. Remember that very large positive delta H is going to cause our delta H here to be very large positive, which causes our delta G to also be positive, and therefore no solution forms. So that's our answer. Okay, so that takes care of kind of our solutions. Let's talk about the colligative properties of a solution. And I'm going to go through this fairly quickly because we did do colligative properties last year. And keep in mind on the AP exam, the calculations of colligative properties is not actually present at all. So what do you have to do with colligative properties? You have to know the concepts, which you really already do. So let's just kind of review. What is a colligative property? A colligative property is a property of a solution. So this is our boiling point and our freezing point, as well as our vapor pressure, which we did not talk about last year, but we're going to talk about this year. And it's the changes in boiling point and freezing point and vapor pressure due to a solute being dissolved in the pure solvent. So if you remember last year, we did the freezing point depression lab, and I believe we took water and put urea in it, and we measured the change in temperature. We also did the slushies in the sink. And those slushies formed because of the fact that the water was able to get to a much lower temperature and therefore freeze the Kool-Aid. So that is a colligative property. It's the change in freezing point, boiling point, vapor pressure, and also technically osmolality, but we don't talk about osmos in AP chemistry. That's more of a bio thing. So just remember that boiling point is going to increase, freezing point decreases and gets lower, and then vapor pressure is going to decrease as well. So let's talk about these and kind of review a little bit. So vapor pressure is one of the ones we did not talk about, and it's called vapor pressure lowering. So what we have to remember is anytime a solute is put into a solvent, we're going to increase the amount of intermolecular forces. This increase in intermolecular forces is going to cause what we see in terms of our properties. So vapor pressure, remember, is the amount of gas able to escape from the liquid in the solvent, the pure solvent. So the amount of gas that's able to escape from the solvent. So water vapor above the liquid water is our vapor pressure. And the more molecules we have floating around, the higher the vapor pressure. The less molecules we have floating around, the lower the pressure, because remember, pressure is the amount of collisions. Okay? So with that being said, if this is our pure water and we add, let's say, sodium chloride to the mix, okay, what's that going to do? Well, it's going to increase the intermolecular forces. By increasing the intermolecular forces, it's now going to require more energy for the water molecules to be able to escape the liquid phase and turn into the gas phase, which means less are able to do so, and we end up with less molecules above the solution and therefore a lower vapor pressure. Okay, so by adding more intermolecular forces, it makes it harder for the species to be able to escape into the gaseous phase, and therefore, because you have less molecules floating around in the gaseous phase, you have less collisions against the walls of the container, and therefore, lower vapor pressure. Okay, all right, let's talk about boiling point. So, two ways to look at this. First and foremost, the simple way to look at it is boiling is going to require intermolecular forces to break. And again, we just increase the amount of intermolecular forces because we now have a solute in the solvent. So we have more intermolecular forces. So because there's more intermolecular forces, it requires more energy. And therefore, because it requires more energy, it results in a higher boiling point or a higher temperature. But the proper way to look at it is remembering back to our definition. So remember, vapor pressure and outside pressure must be equal for a liquid to boil. And that was, we talked about that a little while ago in one of the videos. So the idea behind this is because we lowered vapor pressure, it's now going to take longer for vapor pressure to equal the outside pressure. And because it takes longer for vapor pressure to equal outside pressure, it is going to take longer to boil, resulting in a higher temperature to boil. And again, we're not actually going to be using this equation at all because we're not going to be doing any of the calculations. We're just doing the basic concepts. Okay? Freezing point. So why do we add salt to the roads when it's cold outside or when we're worried about there being snow or ice? Well, it's because it lowers the freezing point, and therefore it's going to remain more of a slush on the roads versus ice on the road. So what's actually going on here? So remember, solids have to form a lattice structure. Well, if you have a solute in the mix, it's going to disturb that lattice structure, and therefore it's not actually going to want to form. And because it doesn't want to form, it's going to have to be forced to form, if you will, and therefore it must be a colder temperature to actually cause the lattice structure to be able to form, and therefore we end up with a lower freezing point. So basically the solute is disrupting the intermolecular forces. So we have an increase in intermolecular forces, but the intermolecular forces we want to form the lattice structure of the solvent, the solid solvent, it's not going to want to form, and therefore it's not going to. Or it's not going to at that temperature. We have to make it even colder to force the intermolecular forces of the lattice structure to form. So we end up with a lower freezing point. Okay? Okay, and we end up with our phase change diagram. So just kind of take a second to look at this. I'm not going to spend a lot of time on it. The blue is our colligative properties and what it does to our phase change, and the pink is our original. So just kind of notice the spreading of it, and that's about it. Thanks, guys.